public talk the day after Valentine's. Today we have with us Professor Audrey Moores, who has been a professor at McGill for 15 years in the Department of Chemistry, and we hope that she could share her love of chemistry with us today. So this is going to be a standard talk style public talk where our speaker is going to talk for about 45 minutes. And then after this, we're going to forward your questions to her. So if you have any questions that should pop up in your mind throughout the talk, please put them in the Zoom chat or YouTube chat or comments. And at the end or during a pause in the middle, we can forward those to her. And this talk is supposed to go until 8 o'clock, so that gives us about 15 minutes for questions. And so we're very excited to have our speaker, and I'll let her take it away, giving us this talk about green chemistry.
Hi, thank you so much, everybody, for joining today. And what I'm going to try to do is walk you through a journey on chemistry and tell you a little bit about how in chemistry we think about giving energy to our systems. So when I think about chemistry, I think about transforming stuff. And for instance, one important transformation that comes to mind is the fact of turning oil into soap. This is something that we've learned to do for thousands of years. This is chemistry that is very intuitive to a lot of people. And it turns out that when you do this chemistry, you need to deliver a little bit of energy to your system. So this could happen by heating up your system. For instance, this is something that we know to do, for instance, when we do cooking, which is a lot of chemistry as well. So this diagram in the middle shows you an energy profile where the starting material, for instance, this oil here could be seen there. And as it reacts and becomes soap, in fact, it goes through this profile of energy here where it has to go through a higher stage in terms of energy. So what this means is that when I want this transformation to happen, I need to provide my system with enough energy that the transformation can happen. So essentially that you can go over this energy barrier. This is a concept that's very common. A lot of chemical transformations require this energy for happening. And if you look at chemistry out there, there's a lot of stuff that can deliver chemistry to you. So just mention heating, this idea that you put, you're going to put a good fire underneath and it's going to make the reaction go. This is the most traditional way that we're thinking about chemistry. Still a lot of processes happen through thermal. But
sorry, Professor Moores, it appears that the audience can't see your screen, so we're trying to fix that.
Okay, let's see. So on my Zoom, it looks like I'm sharing, and it looks like I'm sharing what I should. Do you want me to unshare and do it again?
Yes, let's try. Oh, yeah, okay. Try sharing it again.
Okay, so apologies for that, guys. I'm not sure what's happening.
It might have been a problem on our end too, so we apologize as well.
Is it better now?
Yes, okay, they're saying it is better. So
yeah, it does say that participants should be able to see it. So I'll just show you that, right? So this is the oil to soap transformation. And this is the energy profile that you have where you need to go through some energy barrier, and you need to give energy to your system so that the reaction proceeds. So as I was mentioning, you can do this thermally, so you can heat your system to pass this energy barrier. But another common thing you can do is you can actually use photochemistry. So you can use photon in order to provide energy to the system. A very good example is photosynthesis, what plants do in order to grow and make chemical transformations. You can use electricity as a way to deliver the energy. You can use as well things like microwaves or sound waves, sonochemistry. And more recently, or maybe not that recently, it's actually a very ancient way of doing things, but it's become really popular in the last 10 years in particular to start doing chemistry with mechanical force, so delivering energy to your system by milling or hammering onto a material. And this is what I'm going to try to talk to you about today. So there's a number of devices that would allow you to do that. So this is just examples of stuff that we can find in the lab to deliver mechanical energy in the system. We can use the good old modern pestle, a pestle that you probably use in your kitchen, but we could use mechanized version of it, either through the planetary mill, which is this thing that has 4 reactors that turns around. Or you can have vibrational mills here, so this thing is kind of vibrating back and forth. You can use also extrusion, which is a force of delivering shear force into your system, so it's a mechanical force activation. And as I mentioned today, you can also use aging. So this is this idea of combining mechanical force in the solid phase and then let the process happen through aging. So I'll mention all of these today. This concept of mechanochemistry has become really popular. And in fact, 3 years ago, IUPAC decided that it was so awesome that it deserved to be named one of the 10 inventions that will change the world. So IUPAC is our global organization for chemistry. They decide, for instance, the names of chemicals. So they're very important, and they decided mechanochemistry was important too. So this is something that's really cool. We have an expert in mechanochemistry at McGill, and when he joined McGill about a bit more than 10 years ago, he actually brought with him a lot of this knowledge, and this is how I started to do mechanochemistry myself. So that's Thomas Lafritish, my colleague from chemistry. You can see him here with a mechanochemical jar in his hand. And some of the questions that we often have when we talk together is, what is mechanochemistry exactly? How does it work? How much energy does it give? And is it a lot of energy that is given? So what I'm going to talk to you about throughout this hour that we have together is trying to capture how much energy this gives, and in a way trying to understand what type of chemical transformation we could do with that. So I'm just going to show you here an example of a mechanochemical transformation, if it allows me to click on it. Give me a sec here. So this is a jar that is moving back and forth 30 times a second, 30 hertz. And it's been, the jar that is in it is made of transparent plastic, so you can see through. And it's got a couple of balls inside, and you can see that the shape that it's making in here is very much an H shape. So the concept that you have here is a jar in which you have the sides being round, and you have a bowl that is constantly molding your material constantly in a very precise and controllable way. So it's really about this concept of a mechanized modern pestle. So if you think about it, it's not that much energy. But what I'm going to tell you today about is how much this low amount of energy delivery can actually mean a lot in terms of being able to deliver the right amount of energy and do the chemistry that you want to do. So mechanochemistry is used in a number of different areas, but for instance, for making pharmaceutical, it's become really big. And a lot of the knowledge that we have of mechanochemistry comes from making drugs with it. So you'd be really surprised to know that a lot of the ways your drugs are delivered to your body is through co-crystals of a drug with another inert molecule. And that the way these co-crystals are organized determine a lot of things about how the drug can be delivered. So mechanochemistry, in order to make these kinds of co-crystals, has become a really big field of research, and it's something really, really interesting. Another thing you can do is you can combine the concept of using mechanochemistry in the dry form, so mixing powders together, with mixing powders with a little bit of solvent. So what mechanochemistry allows us to get rid of solvents, which is really cool because it's a huge waste in chemistry, the solvent. But at the same time, sometimes you need a little bit of it. And what we found more and more is that just adding a tiny bit of solvent can actually completely change the chemistry. So these are examples of how tiny amounts of reagents in different quantities can completely change the outcome of a transformation, which is pretty cool. And finally, I mentioned this concept of accelerated aging or aging, which is this idea that you can let a powder sit after having been milled over time, and do so. It could happen under a little bit of heat, 40, 50 degrees. It can happen in the presence of a solution that's going to deliver high humidity levels inside the chamber. And these are going to really help the reaction happen. And we really find a lot of really cool systems enabled by doing a combination of mechanochemistry with AJ. So now that you have all the toolbox with you, I've shown you a lot of the things that we're going to talk about today. Let's dive into the problem that we had when we started looking into it. So I'm a chemist who's been making nanomaterials. This is what I've started to do during my PhD, and I just loved it so much that I stuck with it. Nanomaterials are simply materials that have at least one of their dimensions in the nanometer region. So from 1 nanometer to 100 nanometer and a bit more. The materials that you can make at the scale actually could be any material. So you could use a metal like this guy here, the gold nanoparticle here. You could use organic matter like soap, for instance, coming back to the notion we had at the beginning of the class. You could have liposomes, which are biology made nanomaterials, carbon nanotubes, and so on and so forth. And right now, these types of materials have really hit the market, and it starts to be applied in a huge number of applications, going from medicine, imaging, therapeutic, optics, electronics, catalysis. They're really big in processing chemicals, but also sensing, food, agriculture, or depollution. So this is really something really far-reaching, and a lot of different markets are deeply affected by the entry of nanomaterials. One issue that you find in this field is that making the nanomaterials is really, really difficult to do, very technical, sometimes difficult to scale, and difficult as well in the sense that it's going to yield a lot of waste and a lot of potential pollution. So there's a lot of interest in looking at how nanomaterials are made and how you can make that better. There are two big ways you can make nanomaterials. You can do it in a top-down approach. So you can start from a piece of metal, for instance, and you grind it down. This is very much mechanochemistry, but with a lot of energy. You can grind it down to the nanoscale. When you do that, you need at the end to stabilize your particles so that it doesn't start to de-agglomerate. So you can do this with different molecules here. You can see them in blue. But so that works, and you can put it at a pretty large scale. I mean, people know how to do that at the ton scale level, but the issue is that you're not making really nice particles. They typically have inhomogeneity in size and shape, so it's not really ideal. Another approach is to start from the metal atoms and try to combine them together in a controlled way until they have the size you want, and at which point it should be stabilized by this capping agent. This is what we call the bottom-up approach from molecule to nano. And that's something really cool, but it requires a lot of material, it's very wasteful, and it's extremely hard to scale. So again, what I'm talking about today is not about grinding down bulk precursors, which we know how to do, but I'm going to tell you how we can use mechanochemistry to, in a solid phase, build up nanomaterials from a low energy delivery of energy with mechanochemistry techniques. So what we do is we will use atoms of elements and combine them together with a capping agent and form nanomaterials. So the concept here is really moving away from what we do where we usually use a solution, and it requires typically really dilute conditions. This is, again, really wasteful. Instead, using no solvents and making them grow in a solid phase in a controlled fashion. And when we do that, we change the way we deliver the energy from a purely thermal one to a mechanochemical one. Or should I say, privileging shearing effects, like in this good, again, old traditional way of making olive oil, again, to keep the theme of this talk. So we've been working on this for a while, and we were able to demonstrate that we could make gold nanoparticles, for instance, by using this method. So mixing some precursors, some ligand stabilizers, and we managed to actually control their size really nicely. And they're really small, like 1 nanometer a nanoparticle, a diameter. This is really difficult to do in the liquid phase. So we were able to do this with very good control. We could scale this process to a few grams, which was really, really cool. And then we moved on and tried to make composites. So in this case, we mix metals with a biomass-based material, lignin, and we make this lignin infused with metals. And that enabled us as well to make a system that can deliver antibacterial activity in a filter that works in less than a second. So you can pass through filters containing this lignin and nanoparticles made by mechanochemistry. And you can kill completely these 5 different bacteria, again, in less than a second with really high efficiency. And this process was really nice because we could make the filter with a very limited amount of resources. You just needed a bit of silver salts and lignin that you can take from trees around you. So we continued moving on and trying to develop new concepts around this. So I mentioned using metals here, so gold or silver or ruthenium. Well, we started to think, okay, how about we make nanomaterials with multiple compounds together? So this is, for instance, making bismuth sulfide materials, which are really important for cancer detection, so for theragnostic. We worked really hard on this, and we combined different precursors of bismuth. You can see this here, different precursors of sulfur. We were milling them together. And when we were working on this was work by Malk Malka in my group. He was milling things together, and we couldn't really make nanomaterials. And so one day he forgot his sample, left it on the counter, and when he came the next day, the white powder had turned completely black. And what we realized is that we needed to leave the reaction for some time, so up to a day, for the reaction to complete itself. And then when we let this happen, we suddenly see nanomaterials. You can see them here. You can really see nice small nanoparticles of around 2 nanometers. And what was really cool about this process is that it was super resilient to a lot of different functional groups that we could put on the surface. So this green thing around the particle is the ligand, and this determines the properties of the particle. If we can solubilize them in water, for instance, which is really critical to inject them in the body and use them for cancer detection, for instance. So we could demonstrate that we could, in one step, get them to be functionalized with these different molecules, in particular these 2 ones, which make them soluble in water. And just to keep a mental note about this, if you make them by the traditional chemistry methods, you would require 3 steps to get to the functionalization with this guy. So that's really cutting a lot of waste and a lot of energy in the process. So eventually we could determine that we could do cancer detection with them using this CT, so at least detection, sorry, correlating the quantity of the material with the response in a CT scan experiment, which was really, really cool. Another application that we did was to make nickel phosphide materials, these kinds of materials. I'm not going to walk you through all the details here, but just again, to show you by careful choice of ligand, careful choice of precursors, we could make this nickel phosphide nanomaterials. You can see them here. These are the dots inside this material there. And what was really cool about this is that these materials could be combined with some photoactive material here, which is depicted in red, and we could make something that was pretty good for water splitting reactions, so making hydrogen from water. So these systems, the way they work is they absorb light, and then the nickel phosphide acts as a catalyst to cut the water molecule in two and make hydrogen, which is pretty cool. So we've developed that, and we've been really happy about this. And essentially what we can say here is that if we look at the making of nanomaterials, which you can make in a solution-based method, what mechanochemistry has brought to us is an opportunity to make new nanomaterials, explore new phases of this landscape of nanomaterials that we have. What's really interesting is that in a lot of the examples I showed you, they tend to be smaller than your one you make in solution, which is very counterintuitive to us. Because everybody said, oh, mechanochemistry, you deliver a lot of energy. You're going to make, more stable materials. Turns out it's not true. We're making materials that are difficult, if not impossible, to make via solution-based methods. So this is also something really interesting to us. So more recently, we've been trying to say, okay, we've been making these nanomaterials, but how does it exactly work? What is the mechanism for these transformations? And a number of groups around the world have also looked into this, and here are some colleagues who have said, okay, let's try to monitor, follow the reaction of reduction, for instance, of a gold precursor to gold nanoparticles by ball milling in a solid phase, and follow the reaction to understand how the reaction progresses over time. And this is what you see here, so you can understand and track in time how the particles, the gold, certainly goes from gold 1 or reduced gold, gold ions, all the way to reduced gold here, which is the nanoparticulates. So we're really interested in this, and we thought, oh my God, we need to understand that better, and we need to model how nanoparticles can go from molecules, atoms, all the way to nanomaterials, which contains now dozens or hundreds of atoms. So we partnered with Nick Pravatas, whom I'm sure you know in your department, who's an expert in phase fill theory, which is a very interesting model in order to understand how phases transition happen and things change phase. So this is what we have here. We have the change of phase from a system where we have essentially diluted ions to a system where we start to have nanomaterials that appear. So this is again the first thing I showed you about making gold nanomaterials here. This is the transformation, and what we're trying to do is really model this transformation where we imagine having gold 0 spread in the system and then turn it into assembling itself into nanomaterials. So we've used the model developed by Nick and Lynn, and we've used that to try to understand a little bit better what we have. So as we grow these types of models, we can understand, for instance, the way the nanomaterials form, so we can actually compute them a certain duration. And so what we're doing with this is that what we're able to do is we're able to go to understand the phase transition between a state where we have the gold that is spread all over the place, and then it will go through this activation energy, so this transition phase, and then start to form the nanoparticles. So in this case, the gold and the organic phase are quite well separated. In this case, they're all homogeneously mixed together. And what we found is that we're getting really interesting results for the phase fill theory of Nick and Lynn. But then we realized that if we were adding mechanical force inside the system, which is something we can do by adding a ballistic term, something developed for neutron bombardment reactions, we could actually get a better handle over the energetics of this and actually lower the activation energy to demonstrate that the reaction could be feasible, and also making the materials more stable. So this is the green curve here with the mechanical force that actually describes better what we observe experimentally. So that was really interesting to us to see. We also could correlate some of the observation that I sort of tried to show earlier, where the ligand size actually matters in terms of the size of the nanoparticle that you make. And you could also correlate that very nicely with the model, understanding here that the one in green, which is the lowest one, so the one that's the most stable, happens for the longest chain, which also corresponds to the smaller particles. And we could correlate with the model that we also do observe smaller nanoparticles doing that. So that was really cool. So I'm just gonna sort of go for a pause here and try to sum up a little bit what I've been telling you. So we have demonstrated we can make these nanoparticles by solvent-free methods. We've tried to understand a bit better how they're made through phase fill theory and the addition of this ballistic term. And we've found applications, for instance, I mentioned the antibacterial filter, cancer detection, and water splitting. I'm really thankful for my coworkers here. I'm going to acknowledge them at the end, but this is kind of a nice time to maybe take a few questions, because I'm going to then segue into a slightly different topic. I don't know if someone wants to ask a question at this point, or if I could just read from the chat box.
It appears that we don't have any questions so far, so we'll just allow you to.
No problem. Okay, so I'm just going to move on, and then you can let me know at the end. So what I've been showing you up to now is how we could make these nanomaterials by solvent-free method, and really try to gain both on the side of making better nanomaterials, and also at the same time we save a lot of energy and chemicals in doing so without the need of a solvent. So let's go back to this example here where we've been making bismuth sulfide with this method. So this is a fun story. This is one summer I was working with Mike and Thomas Lab on this project, and we hired an undergraduate student, Pierre-Olivier Farcombe, who was interested in mechanochemistry, and he was wondering, this ligand that you can see here is the ligand that's essential for this process. And Pierre-Olivier was about to buy it so that he could make his transformation. And he was like, oh my God, this precursor is really expensive. And we were like, yeah, it's true. And we couldn't really quite understand why it was so expensive, because this is just a polymer, but it has this functionality, this amine at the tail end of it, which was critical for the application we had, but it's also the reason why it is expensive. It's difficult to make this molecule, this long polymer with an amine just at the end. So he said, you know what, I'm going to spend the summer trying to make a mechanochemical synthesis of this guy. So essentially, he went out there and he said, okay, I'm going to make this polymer and it's going to be really cool. So again, you guys are not chemists, so it's not really important. I'm sorry, there's a lot of equations here, but essentially this is PEG. It's a polymer that we find around ourselves, very useful for a number of applications. And what you can do with it is you can change its properties by changing this N group here. Here it's an alcohol, and you can change it for this guy. It's called a tosylate. You can change it for a bromine. You can change it for a thiol, or for these functionalities here, and you can change it for an amine, which is what we wanted to do. Turns out that Pierre-Olivier was able to develop this chemistry with very good yields, very nice. So this is really a pure organic chemistry paper. We published it in this journal. And it was cool. It was fun to do that. But I really wondered, okay, this is really interesting, because I didn't want to touch too much polymer chemistry, because I thought, oh my God, the polymers will be damaged when you hammer them with stuff. Turns out the polymers were fine. We did the functionalization very well. We have very good yields. So it was like, okay, this is interesting. Another completely different example. This is Alan Lee from my group, who was working on some transformation. Again, I'm not going to go into the detail, but he managed, using this chemistry he had developed, to transform polyketone, which is this polymer that's used as a thermoplastic, which is completely insoluble in most solvent. He turned it into a polymer with different functionalities, now a little bit more soluble in aqueous solvents. And again, he did so by mechanochemistry. He was actually, milling it for some time, and again, no damage done to the structure of the molecule. So we're like, wow, this method is really interesting. We can functionalize polymers. We could make transformations that are difficult to do in a solvent, but we could, it's really cool. Can we look at a really important problem out there and try to apply this to solve it? So we came across this problem here. So this is a big question right now, because I don't know about you, but I hear all the time that we need to get out of fossil resources for making stuff around us, right? You agree with me. We need to stop making plastics from fossil. I mean, okay, who does that? Everybody, but we need to stop. So people came up with this idea that instead of using fossil to do stuff, we should use renewable materials and biomass. So biomass is essentially plants which are made of polymers. I'm showing you the structures of some polymers. Again, it doesn't really matter the structure, but they're polymers. So this means there are long chains of repeated units over and over and over. Or you have also chitin, which is another polymer that you can find this time in insects or in crustaceans. And what people are doing with them in general is they take those guys and they take, okay, we're going to chop off this polymer into very small molecules, which act a little bit like Lego blocks. And once we do that, we can recombine them and make new materials that would be interesting and that we typically make by fossil carbon these days. So that's all good and well, and there's huge amounts of efforts that are made in doing that. But one thing that I was really interested in is, people will also try to do this to make plastics, so to make new polymers. So the concept here is that you take a polymer, you break down the polymer, you remake polymer. doesn't make complete sense to me. So can we try to figure out if we could use biomass directly, functionalize it to make molecules we want, and bypass these very, very costly steps that are going on here? Okay. So this is where mechanochemistry can really bring something. So we started to look at the scale of the problem. So I mentioned Christosine waste and this chitin molecule, very interesting molecule. It turns out that it's coming from waste from crustaceans, and it turns out that we make huge amount of it every year. So there's between 6 and 8 million tons of waste of crab, shrimp, and lobster that are produced on a yearly basis. This actually, by the way, is kind of the scale at which we generate plastic waste that goes to the environment. So the scale here is relevant, and it's actually important to try to see if we could do some stuff with it. What you can do with it today is turn this shell of crustacean into a molecule called chitosan. And the way you do this is that you do it with a lot of chemistry. So today, people will take the shell of crustaceans, which is essentially made of 3 different compounds. The compound in blue here called chitin, some minerals that are on the surface of it, and proteins that are lacing stuff around. And what you can do with that is you can extract it, so add some chemicals to sort of have pure chitin and get rid of the rest. And then you can do even more chemical treatment to turn this into chitosan, which is this molecule here. Turns out that one issue is that, it turns out that the issue there is that the chemistry that you need to do this is pretty harsh. You need to add really corrosive liquids under very viscous conditions, high temperatures, and these conditions are so bad and the amount of waste generated from it is so high that today in Canada, although we produce a huge amount of crustacean waste, today in Canada, there's no plant doing that process because it's just too wasteful. It doesn't work out. It's a shame though, because this chitosan material is really useful for making water filters, sutures, or antibacterial materials. So it would be really cool if we could do this because we have this resource and we're not exploiting it. So some folks have thought about doing it by mechanochemistry before us, but they were really focused on turning this material into really small portion of the polymer, cutting it into really, really small portions. So what we looked into at my group was how can we take the chitin material that you have here and turn it into the chitosan that you can see there and do it without breaking out the polymer too much, again, protecting the polymer as much as possible. It turns out we found a way to do it by mixing milling that you can see here with humidity aging. So letting the powder sit under high humidity and let the transformation happen. When we do this, we found that we can retain really long polymer chains, which are really important for a number of applications. The really cool aspect about this is that we could use all sorts of sources of crustacean to do this. We could use shrimp, lobster, crab, or even insects and still get really very high quality results. What we could do as well is we could reduce massively the amount of energy needed for this transformation. So when you look here at the yellow line there, this is the process that we do under normal chemical condition. If you use any mechanochemical version of this at the bottom, you save a huge amount of energy, as we can see. So this is really cool. We use also far less chemicals and far less water, about 1 order of magnitude less water. And this is what gets people really interested and exciting because this is the key to making it potentially commercially viable in Canada. So what we've done doing this is we've opened the path to new material chitosan with high molecular weight, and we do this by mechanochemistry. So this is really, really interesting. I don't know if I have a lot more time. So I'm gonna walk you through a little bit more of that chemistry that we're doing, and I'm gonna tell you a little bit about another type of material that we make with this. So I mentioned earlier that you could take the crustacean shells and you can extract the chitin and go to chitosan. But another thing that you can do is you can actually break apart the chitin and release some nanochitin, which is now the same material as this one, but it has It's highly crystalline and it has the form of whiskers. And what this material allows to do is to, so the material looks like this, looks like little whiskers there. And what this material allows to do is to make all sorts of films that have optical photonic properties and stuff like that. We would very much like to make nanochitosan because it would also have this additional benefit of the antibacterial properties that I mentioned earlier. But unfortunately, it's very hard to do because when you have nanochitin and you start treating it to make chitosan, it completely loses its nice whisker shape and all its properties for making gels and films. So one first question that we had is, can we make the nanochitosan? So I have a really nice collaborators from NRC who's developed that chemistry. And again, I'm not going to walk you through all of this, but just to tell you that essentially he was able to break this paradigm and actually find a way to make nanochitosan. So you can see the nanochitin here and the nanochitosan there. So that was kind of cool. In my group, we were interested in those guys and we started to exploit them in catalysis. So we just took the nanochitin or the nanochitosan, put some gold on it, and we did some transformations just to validate that we could do some work with them. But we did the same with palladium. So again, very chemical oriented. So skip with that. But then again, we were interested in knowing, can we use mechanochemistry to make this transformation? So I had a student who worked on this and she found a way to actually go from the nanochitin that you can see here to the nanochitosan that you can see there. Again, using mechanochemistry in very nice and mild condition. Again, doing this compared to the process developed at NRC, we save a lot of energy, we save a lot of molecules, compounds that we add to the system. One really cool thing that we did with this though, is that we managed to make some really cool hydrogels. So what we did with that is we combined the nanocrystals that you can see here in yellow with another biopolymer called alginate. And that allows us to form these really extended networks. And it turns out that they have really nice properties in terms of toughness. So we can make materials that are now hydrogels that are now have very nice mechanical properties. And in fact, for these kinds of material, the highest shear modulus that you can find on. So you, in fact, the storage modulus, sorry, and the loss modulus were the highest for comparable materials. So that was really cool. And we decided to apply this to some drug delivery. So we used this bovine serum albumin here as a model for a drug, and we combined it with the elements of this hydrogel to make the gel. And we could make these nice beads that you can see here. And then what we did is we measured how long it took for the drug to be released over time. And we found again that the nanochitosan that we had made was really high in enabling to slow down the release and make a drug release that was very sustained over time, so that you can make implants that are going to very slowly release the drug over time. So we went from release in hours to release in days, which is really starting to be interesting as well for applications. So overall, what I was showing you here is how we could use this crustacean waste and actually turn them into some really useful materials. I mentioned how we could make chitosan. So if you want, I can tell you more about the kinds of applications that we're looking for on this side. And on the nano side of things, we've been showing how we could make hydrogels that have enhanced mechanical property, but also biomedical applications. We could make gels, and I also showed a little bit of catalysis with them. And finally, I just wanted to show you a little bit where we're going with this process in terms of scaling it up and starting to apply this. The first project that we did in trying to apply this a little bit more to the real world has been with Parks Canada, and in particular, a really nice park in Nova Scotia called Kijimkujik Park. And these two wonderful individuals, Gabrielle Beaulieu and Chris McCarthy. And the problem that they have in Kijimkujik, so this is about 2 hours down from Halifax, you can see it here. They're invaded by green crabs, which are eating up all their ecosystems. So they are all the time harvesting all of these crabs. Here, I can show you, those crabs are really cute. They move really a lot. And when you go there and you fish for them, really harvest a lot of crabs. So at Kijim Park, they have developed a pioneering program where they actually keep harvesting the crabs, and they've really recovered a lot of ecosystems thanks to this effort. But the counter side to it is that they have now this crab that don't know what to do with. So we've managed to demonstrate that we could take the crab waste. So this is the green crab when it's cooked, so it looks more red now. And we've managed to demonstrate that we could turn this into chitin and then chitosan in really good yields, and we demonstrated that it was working really, really well for this. The next step for us is now to work with a small company in the north of Quebec with Marc Fafard from L'Eau Rouge. We got some funding to start to do a scale up on this process and understand how what parameters we could do to, in the long term, start building a plant to harvest and convert the, million kilogram plus that we have in these 3 ports, 3 harbors alone on the north of Quebec. This is just the amount of waste that they have just for crabs. So this is really something interesting, and we're going to continue working with them in the near future. So I have to thank a bunch of colleagues with whom I've worked on this. So I want to acknowledge all these folks: Monica, Georgia, Lynn, Blaine, and Michael, for all their work over the years on the nanoparticle side of things, and Thomas Lafritich and Nick Provedas for being amazing collaborators. And on the biomass side of things, so the polymer side, I really want to thank my students on this, in particular, Tony, Tracy, Shribine, and Faiza, whose work you've seen today. This is my, again, amazing collaborators, Jan Yu from McGill and Edmund and Davis from NRC. And this is the Chitotim, as we call it now, with some of the waste from crustacean that we are receiving on a regular basis in the lab. So I want to thank a bunch of people. People are acknowledged here, and I want to thank you very much for your attention.
And thank you very much, Professor Morse, for the fantastic talk. So we do have some questions here that I could forward to you.
Cool, go ahead.
So the first one is, are there waste products associated with extracting the chitin from the crab or shellfish shells?
Yeah, that's a great question. So indeed, there is a waste product. So what happens is that in a crustacean shell, you would have between 15 and 30% of chitin, and then the rest is composed of proteins and also minerals, so especially calcium carbonate. So what you can do is you can harvest those, and actually you can recover those as well. One big issue, though, is, well, not a big issue, but one thing to consider, though, is that the chitin and the chitosan are the one with the highest values. So although they don't constitute more than a third of the volume, they actually sell for, 1 order of magnitude more, for instance, than the calcium, let's say. So this is really interesting to do that.
All right, thank you for the answer. There's another question that's more generally about chitin, and it's specifically its color. So we'll see how. Yeah, so it says, is chitin red colored, or does something else generate the color of the shellfish shell?
This is an excellent question. So the color is coming from a pigment called axaxanthine. I think I always massacre this word. Sorry. And it's actually a pigment with high values. So although there's only a small percentage of it inside the shell, if you harvest it, you can actually sell it at a good price. So this is something that people could do as well. And this is something that we're thinking about doing, because one of our strategy in the long term is to really think about this as a circular economy. And what we would like to do eventually is also harvest the proteins and harvest the minerals and also this dye, because it sells for a good price as well.
Okay, very interesting. There's a question here, I think referring back to mechanochemistry. What is known about why mechanochemistry is able to produce certain molecules that regular chemistry with a solvent cannot? Or is that something that's just been observed?
Yeah. So it's a very good question, and there's still a lot of research going on in this area, and there's still a lot of questions that are unanswered on this. So what we know is that mechanochemistry tends to, in terms of the kind of reactivity you can do as compared to solvent-based, it's similar because the kind of energy that you have are in the same order of magnitude, I would say. But what you find is that mechanochemistry can proceed with different pathways. So you can, there's a number of examples where people showed that they could make products that they cannot make in solution. And that I think has more to do with not so much the ability to break certain bonds that mechanochemistry would have and not solvent-based chemistry. It's rather because you can actually stabilize certain organization of matter that in solution would not happen. And there's still very much of a question mark about why this is happening, but this is what we see. So there are reactions where in solution and mechanochemistry it's the same, and there are reactions where the selectivity completely changes in mechanochemistry, and people are still trying to figure out what are the rules of why a reaction is in one category and why another one is another category, and also how can we predict that and start to build rules around it so that we could start using them more systematically. So that's a very good question indeed.
Thank you for the response. We have another question here. So is there a more sustainable solution for gathering shells? It sounds like gathering waste from crabs that are overflowing might not truly be sustainable or could lead to farming.
Yeah, so that's a very good point as well. So, if you are considering the current situation where people eat crustacean for food, for their sustenance, the shell is generated from that activity. So right now the shell is the waste. The shell is happening whether you like it or not, and it's there. And then the question is, do we use it or do we not use it? But I don't think right now we have a situation where overfishing, for instance, is happening because somebody wants chitosan somewhere in the world. It's not the case right now. We're really far from it, if anything, because a lot of the waste is not transformed. The other thing I would say is that today, what happens is that people will fish a lobster or a crab. Typically, a lobster will be shipped to the place where it's eaten as a whole. So people will eat whole lobster, cook whole lobster, and then that waste is wasted because we're not going to go in every house and collect like the few lobsters they eat on a yearly basis. It's not sustainable. But the crab is different because a lot of the crab is actually cooked and processed in a factory, and then the waste is generated there in high quality. So this is a huge opportunity that you could seize. And this is typically what's happening in Quebec. So you have the numbers I showed you are for crabs for a reason, because this is really where the opportunity lies. So right now you have these plants, they exist, they process crab, they sell crab, and they have the waste and it exists and no one does anything with it. So that's why it's sustainable, because you have a waste that exists today, and instead of dumping it, right now, some folks dump it in the ocean, which is really bad. Others will dump it in the landfill, which is another bad thing. So really, another thing that people can do is do some composting and then use it for farming, but it's not going to be as efficient as some of the solutions that we're providing.
Okay, good to know. The next question that we have here is, how do you determine the recipe to convert the materials that you have into your functional materials? You mentioned times like 30 minutes and 90 minutes as aging time. How are these times found? So
this is not done arbitrarily. We typically try. So when we start working on the process, we will try several times of milling, several times of aging, several kinds of liquid-assisted grinding, several types of reaction conditions. And then we see what works, and then we optimize it from this data. So the things I'm showing here are optimized process, but there's a lot of work going upstream that I'm not showing, where people just like try everything and then figure out what works best.
Okay, thank you. The next question is, what is the interest in forming gold nanoparticles?
Yeah, so gold nanoparticles are really interesting materials. So they can be, they're used, for instance, in detection and theranostic because they can absorb light, for instance, and generate heat locally, which can be really useful for burning tumors, for instance, or for offloading drugs in a controlled drug release platform. You can use it as well, again, for the optical properties in photocatalytic activity, for sensing activity. In fact, they're used in processes where you can detect DNA by a change of color in a process that resembles a bit of ELISA, but that is a lot more selective. So they have a number of applications this way. But making gold nanoparticles on a large scale is very difficult today. So that's the reason why we thought it was interesting to research this area. And our process being scalable, it really offers a lot of opportunity to exploit them in some of these applications.
Okay, that's very cool. We have another question. Is there a general principle behind mechanical being less energy intensive than solvent methods?
Well, so it's not always the case, but it is the case in our system that it works. If you compare them with reaction that happens in a solvent at room temperature, it's not as effective. One of the ways you lose a lot of energy when you use solvent-based systems is that you need to heat all the solvent that is, this heat is lost, right? You're not using it for anything but to convey the energy all the way to the molecule. So this is a lot of lost energy in the system. So what you do here is you deliver energy in a way, I think it really delivers energy in a more controlled way. I think we've shown repeatedly how we can do very soft chemistry, I would say, compared to liquid state. So the energy that we deliver is actually not that much. And this is another way that we do this, is by controlling the energy that we deliver in a fine way. We can also help in this process.
Thank you very much for the response. And it looks like this might be our last question. How quickly are these methods being taken up by industry?
So it's really interesting because in pharma, for instance, they've taken it up for making formulation and making these drug compounds that I mentioned. But it's really interesting because in the same company, the people who are doing the syntheses are not using it right now. So they're calling a lot of folks like me and they say, hey, how does mechanochemistry work? And it's like, yeah, but you can talk to your folks in formulation. They know how it works. So in formulation has been really uptaken. In the food industry, mechanochemistry is used all the time. Think about the things that we grind and mix and knead all the time. So in fact, some of the scale-ups that we're doing right now, we're working with food processing companies because they have the kind of tools to do that type of stuff. But right now, we see in the community a huge opportunity for doing more, I would say, chemical processes by mechanochemistry, and there are some really good candidates right now at the research stage for being scaled. I think there's a lot of work that needs to be done in chemical engineering to scale this to scales that would make sense, and I think this is where we're going to see a lot of the development.
Okay, thank you so much. And with that, I wanted to thank you very much for giving this talk. I want to thank the audience so much for their fantastic questions. And I wanted to
amazing
apologize.
questions, by the way, because I think you guys are just really nailed it. Thank you so much.
And I wanted to apologize to everybody for our unfortunate interruption. I thank you so much for being able to power through that. And I just want to remind everybody that we have more of these in the future. We'll make you could check back in on our social medias or email blasts. So thank you very much again, and good night, everybody.
Good night, everybody. Thank you.